Hello everybody. In this video, we'll learn how to calculate the inverse of a 3 by 3 matrix. Actually, in this video, we have three goals altogether. The first, before we start trying to calculate the inverse of a 3 by 3 matrix, it's important to know if the inverse actually exists. When we talked about the inverse of a 2 by 2 matrix, we learned that they might not always exist, specifically because each term has a denominator, and if that denominator was equal to 0, well, then the calculations fail. There is a similar quantity we can calculate for a 3 by 3 matrix that will tell us whether or not the inverse exists. It determines whether it exists or not. And also, this is related to something we've done before. Second, once we find that a matrix inverse does exist, we'll talk about an algorithm or a process, a sequence of steps for calculating the inverse of a matrix, specifically for a 3 by 3 matrix. In this case, I think it's a little bit easier to go through a process rather than trying to memorize a formula, because the formula takes a very long time to write down. It involves something called an adjoint matrix and alternating signs and determinants, and I really like the process a little bit better, and it's related to row operations, so it ties in with augmented matrices. So we'll talk about an algorithm to find an inverse matrix. Finally, we'll use that inverse matrix to solve systems of equations. In particular, since we're talking about a 3 by 3 matrix, we can use these to solve sets of 3 equations in 3 variables. Now that we know what our goals are, let's dive in. Now, the formula for a 3 by 3 determinant is actually the same, or very similar to, the formula we used to calculate the cross product of two vectors, with the differences that the top row of our grid, when we calculated a cross product, those were the standard basis vectors I, j, and k, and in this case, we would just replace those with numbers. And unlike the cross product calculation, where the result was a vector, when we calculate the determinant of a matrix of numbers, the result is just a single number. So here's how we do it. Let's say we want to calculate the determinant of a 3 by 3 matrix with entries A, B, C, D, E, F, G, H, and I. Well, what we'll do is first kind of pull out these numbers A, B, and C, and we'll write these down here. And we use alternating signs. So A is positive. In front of B, there is a negative sign, and C is positive. And then we multiply each of these constants by the determinant of a 2 by 2 matrix. And in this case, to calculate the 2 by 2 matrix, it's the same process as when we calculated the cross product. The 2 by 2 matrix associated with A, well, to figure that out, we'd ignore all the values in the same row and column as A, and the remaining values form that 2 by 2 matrix. To get the matrix next to B, again, we would ignore the values in the same row and column as B, so ignore those, and the remaining 4 values, in this case, D, F, G, and I, that forms our 2 by 2 matrix, and the same for C. In the original matrix, ignore the values in that same row and column. The remaining values, they form your 2 by 2 matrix. And then, for each of these 2 by 2 matrices, you calculate its determinant. Right, so the determinant of a 2 by 2 matrix here is E times I minus H times F. This next matrix, it's D times I minus G times F. And for this third matrix, D times H minus G times E. And then you just multiply all those through, and that gives you the determinant of the matrix. If we were to write down the formula for the inverse of a 3 by 3 matrix, this would actually appear in the denominator of every fraction that we get. But in this case, we're really just interested in whether or not this is equal to 0, and that tells us whether or not we'll have an inverse matrix. So for example, here's a 3 by 3 matrix, 2, 3, 4, 5, 8, 1, 9, 6, 7. At the 2, the 3, and the 4, we extract those, negative sign in front of the second number, and then we extract the submatrices and calculate the determinants of each one of those matrices. And then we just have a lot of arithmetic to do. And in this case, the important thing is, since this determinant is not 0, this is guaranteed to have an inverse. Right? And if we were to calculate the inverse of this matrix, which we won't, but if we did, the denominators would all be negative 226 before reducing the fractions. But like I mentioned at the beginning of this video, I'd like to talk about a different way to kind of derive the formula for a 3 by 3 inverse and relate it to the idea of row operations in augmented matrices. Now, the key fact in this derivation is going to be that when you do row operations on an augmented matrix, it turns out that each row operation could also have been done through multiplying by something called an elementary matrix. In this case, elementary really means simple, usually mostly ones and zeros, and maybe a single non-zero, non-one number. For example, let's say we start out with this matrix. Let's pretend this 3 by 3 matrix is an augmented matrix. Let's do a row operation on the first row, multiplying the first row times n. In that case, the first row becomes NA, NB, NC, and none of the other values change. Another way we could have arrived at this result would be to take this matrix and then multiply it by this, the matrix N00, 0, 1, 0, 0, 0, 1. Right? It almost looks like an identity matrix, except that first row, the 1 is replaced by an n. And surely enough, if you were to multiply this matrix by this matrix, it's not too bad because of all the zeros and ones. The result would be, the same thing as applying this row operation. So applying this row operation, multiplying the first row by a constant n, corresponds to multiplying by this matrix. As another row operation we often do, we might want to add or subtract a multiple of one row to another. So in this case, starting with this matrix, A, B, C, D, E, F, G, H, I, let's say we want to take the second row and add n times row 1. The result, rows 1 and 3 don't change, but row 2 becomes D plus NA, E plus NB, and F plus NC. That would be the result of that row operation. As it turns out, this row operation corresponds to multiplying by this matrix. Again, it's an elementary matrix, it's mostly ones and zeros, it's almost an identity matrix, except for this entry right here, which typically would have been a 0 if it was an identity matrix, but it's replaced with an n. Right? In row 2 is where the row operation is occurring, and we're multiplying row 1 by n. And so the n appears in this first column here. So this matrix multiplication corresponds to this row operation. And finally, one more example of a row operation, which we didn't really do very much of, but it is a valid row operation. you could just switch two rows of your augmented matrix. That corresponds to writing the system of equations in a different order. So for example, I could swap row 2 to the third position, and I could swap row 3 to the second position. That would turn this matrix into A, B, C, G, H, I, D, E, F. And even this operation of switching two rows corresponds to multiplying by this elementary matrix. Right, again, almost an identity matrix, except some of these ones and zeros were shuffled around. In particular, row 2 was replaced by row 3, and row 3 was replaced by row 2. All right, so the key idea in these examples is row operations are interchangeable with matrix multiplications. And again, this is the key idea we're going to need in deriving a process to calculate an inverse matrix. If you want to perform not just one, but a whole sequence of row operations on a matrix, that corresponds to multiplying a matrix A, by some sequence of elementary matrices, which I'll write as E1, E2, E3, and so on. So for example, this equation right here indicates that I have a matrix A, and then I multiplied it by some elementary matrices. And so 4 elementary matrices, that corresponds to doing 4 row operations. And after applying all of those, the result was the identity matrix. So this equation corresponds to the fact that these 4 row operations turn the matrix A into the identity matrix. However, we also know that if we take the matrix A and multiply by A inverse, that also gives us the identity matrix. So these two equations look very similar. In particular, the I matches up with the I and the A matches up with the A. Remember, I is the identity matrix, and A is the matrix we start with. These row operations correspond to A inverse, right? So if we calculate the product of these elementary matrices, that will give us the inverse matrix. However, that would take a little bit of time, right? First, to figure out which elementary matrix corresponds to these different row operations, and then multiplying them all together. But there is a faster way. So I'm going to take this side of the equation, this left side of this equation, and multiply by the identity matrix. We can do that because multiplying by the identity matrix is like multiplying a number times 1. It doesn't change the value of that side at all. And so this equation is equivalent to this equation down here. We can also interpret this last equation as we've started with the identity matrix and performed a sequence of row operations, the same row operations that turn A into I. Those row operations, if applied to the identity matrix, give us A inverse. So in other words, and we'll do a lot of examples of this, row operations can be used to calculate inverse matrices. So here's the algorithm. And we'll use this for a 3x3 matrix. For a 2x2 matrix, we already have a pretty convenient formula. So first, it's always helpful to check that the determinant is not equal to 0, because if the determinant was equal to 0, the inverse would not exist. Once you know that A inverse does exist, we'll start off by augmenting the original given matrix A by the identity matrix. Right, in the past, when we were converting systems of equations to an augmented matrix, we take the coefficient matrix and then augment it by just a single column of numbers. Here, we're augmenting this matrix by another matrix. So I have a very big matrix M. we'll perform row operations on the matrix M with the goal of turning the left-hand side, this matrix A, into the identity matrix. But we perform row operations on the entire augmented matrix. So at the same time that we're turning A into the identity, we're also turning the identity into A inverse. So once we're done, we have the inverse matrix. And luckily, it's always easy to check that you have the right inverse matrix, because if you multiply a matrix times its inverse, you should get the identity matrix. So that's the algorithm. Let's see it in action. So here's an example. The matrix A is 1, 0, 1, 0, 2, 4, 2, 0, 6. Now we can calculate the determinant of this matrix. And as it turns out, this matrix has determinant equal to 8, which is not 0, which means there is an inverse matrix. So we can proceed. We'll form this mega matrix M by writing a matrix where the left half is our original matrix A and the right half is the 3 by 3 identity matrix. So here's what it looks like. So we have 1, 0, 1, 0, 2, 4, 2, 0, 6 on the left, and on the right we have 1, 0, 0, 0, 1, 0, 0, 0, 1. And now we have to remember how to do row operations. And I'll do a few at a time, just for convenience. For example, we know that the leading number in each row needs to be a 1, which we already have, fortunately. And then every number below this must be a 0. And that's already a 0. That's great. This number right here, we can turn that into a 0 by subtracting 2 times row 1 from this row. So that explains this row operation right here. From row 3, we will subtract 2 times row 1. At the same time, I can also start working on the next row. I know I want to make this 2 into a 1. So I'm also going to multiply the second row times 1/2. After doing that, the first row has not changed. The second row, 0, 2, 4 becomes 0, 1, 2, and 0, 1, 0 becomes 0, 1/2, 0. This last row, so we have 2 minus 2 times 1 is 0. 0 minus 2 times 0 is 0. 6 minus 2 times 1, that's 4. 0 minus 2 times 1 is negative 2. 0 minus 2 times 0 is 0. And 1 minus 2 times 0 is still 1. And we're very close to done, actually. We have lots of 1s and 0s. Next, we'd like to turn this 4 into a 1. So we'll multiply row 3 times a 4th. Right? And that gives us 0, 0, 1, negative 1/2, 0, 1/4. Finally, we use this 1 to eliminate these two values to turn them both into zeros. To remove this 1, we can say from row 1, subtract row 3. To eliminate this 2, we can say from this row, subtract 2 times row 3. When you're done, on the left is the identity matrix. You can take a second to check the calculations here. We'll also verify them on the next slide. But this is what you get on the right-hand side. So this is the inverse matrix. This is A inverse. Now, to check that this is right, we can multiply A times A inverse and make sure that we get the identity matrix. And so we do that here. We'll take the matrix A and partition into rows, the A inverse and partition into columns. And we'll get a lot of dot product-like calculations, partially simplified here. But when you're done, you'll notice that you do get the identity matrix. So A inverse is correct. Next, here's another matrix. It has fewer 1s and 0s in it, but it's not too hard to calculate. Right? To begin, let's see, what can we do with this? We need to get a 1 in this first position, so multiply that first row times a half. Also, to turn this 2 into a 0, we could take this row and subtract row 1. To turn this 4 into a 0, we could take this row and subtract 2 times row 1. Then when you're done, well, we've got lots of 1s and 0s here. That's great. Then once again, we just coincidentally happen to have a 4 in this position again. So we can turn that 4 into a 1 by multiplying the row times a fourth. And we can, we can eliminate this 1 by subtracting row 2 from this row. And now we have lots of 0s and 1s. The last two numbers we need to convert. To eliminate this -1, we could add row 3. To eliminate this 2, we could subtract 2 times row 3 from this row. And when you're done, you have the identity matrix on the left. And all along, we have been doing the row operations on the right-hand side. And that gives us our inverse matrix. To check that it's right, again, we multiply these two matrices together. And once you simplify, you'll see you have the identity matrix. Finally, once you have an inverse matrix, it's very straightforward to use it to solve equations. In fact, the steps are exactly the same as the 2x2 matrix case. If you have a matrix equation that looks like matrix A times vector V equals vector W, and V is your vector of variables, then you can multiply both sides of this equation by A inverse on the left. That will cancel out the A on the left. And then you'll be left with V, your vector of variables, equals the inverse matrix, A inverse, times W, which is a vector of constants. So for example, let's say you have this system of equations. 2x plus 2y plus 2z equals 3, 2x plus 3y plus 4z equals 3, and 4x plus 4y plus 8z equals 7. First, we could rewrite that as a matrix equation. And here's our matrix A. Very thankfully, we just calculated the inverse of this matrix. So, to solve for V, to solve for these variables, we can calculate A inverse times the vector W. So at this point, we need to do a matrix vector product. And when we calculate that, we'll see that x equals 7/4, y equals -1/2, and z equals 1/4. And as usual, it's great to check your work whenever you can. In this case, you can plug the values for x, y, and z into your original system of equations, and sure enough, you'll find once you simplify, you do achieve the expected answers. So we know that this is the correct answer. Now, as an exercise, remember, you learn math by doing math. Here's a matrix. The matrix A is 2, 0, 0, 2, 1, 1, 0, 0, 3. And so it's got lots of nice zeros and ones in there for you, so it's not too bad. Go ahead and calculate the inverse of this matrix, and then check that your work is right. Try multiplying A times the inverse, and make sure you get the identity matrix. And that's how you calculate the inverse of a 3x3 matrix. Thanks for watching.